Hello, this video is for Stat 110, Module 2, Part 2, and includes a discussion of the Helper Hinder case study. Okay, let's go ahead and get started then. So the Helper Hinder case study is a study that took place about 10 years ago, and it was at, I believe, Yale University. And there's a video here that shows the setup of the study, and I will let you watch that video. So go ahead and hit pause here and just watch the video in the notes. Okay, so the setup of the Helper Hinder study, as you just saw, was there were two types of toys. The helper toy, and there was also a hinder toy. The helper toy was, in the video, a gray square that was trying to help the red toy up the hill there. Whereas the hinderer toy was a yellow triangle, and that one was trying to push the red toy back down. Then a tray was presented to the infants with both the gray square, which was the helper toy, and the yellow triangle, which was the hinderer toy. So here's just a screenshot from the video. And we can see that this infant is indeed picking the helper toy. Okay, so let's consider part of the methods section of their article, which was posted on the course website. So the methods section reads here, subjects were healthy full-term infants recruited from the greater New Haven area and were tested at KW Infants Cognition Laboratory at Yale University. So they're giving us just a little bit of information about the subjects that were involved in the study. So the first question that we have here in the notes is, what is the scope of inference for the study? So go ahead and try to formulate a response for what the scope of inference is and type it in the box there. Again, once your notes are complete, you can hit submit your notes, and if you go back, my solutions will be provided for you. So in this study, each child was asked to select either the helper toy or the hinderer toy. The reference distribution is going to be constructed under the situation of no preference. So if a child has no preference, they're going to be picking either the helper toy or the hinderer toy about half the time. So this is going to be a 50-50 scenario. Again, we build that reference distribution under what it would look like if they had no preference. So here I have a couple of input boxes for you to identify what the alternative hypothesis is in words and then also in symbols. And for the symbols, you can just do something like HA is going to be pi bigger than 50%. So you don't have to worry about the Greek symbols there, that's fine. So I guess I gave this one away. This is going to be a right-sided analysis because I want to know if they indeed have a preference towards the helper toy. Okay. I skipped over that up above, but the research question is here, do 10-month-old infants have a preference towards the helper toy? Okay, the setup of the reference distribution then is going to have the following structure. Our number line is going to go from 0 up to 16. If they do not have any preference, then they should be in the middle. This is going to be a 50-50 situation. 16 times 0.5 is going to give me an expected value of 8. So if the kids have no preference, then out of the 16 times, they should be picking the helper toy about 8 times. The outcome from the study here is 14. So most of the individuals, and they said that in the video, selected the helper toy. So here in the table, I have just the lowest possible value, which is 0, largest possible value, 16, What would be the label? That would be the number that picked the helper toy. Expected value is 8. Again, we care about the right side of the distribution. So if they do have a preference, then they should be picking that toy more often. That's why it's right-sided. It is not right-sided because my study outcome is up here. The tail of the distribution has to do with what values support the research question. The study outcome here is going to be 14. Okay, just setting up kind of our table for our hypothesis test. We have our research question. We have the H0 and the HA statements. Identification, what the parameter is. Writing out our hypothesis using that parameter. This is a right-tailed test. My observed outcome was 14. So when I determine my p-value, I'm going to need values as extreme or more extreme. So I'm going to be using values 14, 15, and 16. Again, when I'm determining my p-value, I go ahead and start at the outcome from my study. So that 14 there is going to be put into the p-value box on our reference distribution app. Okay, so I want you to go off and get your own reference distribution. The simulation setup is going to be as is stated here on the screen. Got the helper toy, the hinder toy are my two outcomes. 50%, because this is a 50-50 scenario, under a no difference. They're equally likely to pick either toy. The sample size or number of trials is going to be 16 here. And then again, I put the study outcome in that p-value box. I select right tail. It looks like here I did 5,000 statistics. I would like you to go ahead and embed a screenshot of your reference distribution into your notes. So the following questions down below are going to ask you to use that screenshot. So when you come back and look at your notes, it would be nice if you had a screenshot provided here in this window. So I'll just talk through how to do that. The first thing you're going to need to do is go to the simulation app and obtain a screenshot. So that's going to show up in another tab here. I have that already set up. So go get your reference distribution and obtain a screenshot of what you need. And then go ahead and save that screenshot somewhere onto your computer. So I'll go do that now. So I'm over here on the simulation app. I'm going to set up the success is that they picked a helper toy. Failure is they picked a hinder toy. It's a 50-50 scenario with n equals 16. Going to be working with the counts. I think I asked for 5,000, so we'll get a bunch of dots on our reference distribution here. And I want to figure out the p-value. Okay, so my study outcome was at 14. And then I need to specify that I care about the right side. So the right side of the distribution is what I care about. And you can see down on the reference distribution that indeed the right side, or the dots there that are as extreme or more extreme, are going to turn red for me. Now it looks like 14 is pretty extreme in this distribution. The p-value here is 0.002, which is quite small. So here I've obtained my reference distribution. I want to just take a screenshot of it. And then I'm going to save that onto my computer. So I think I'll just put mine on my desktop, call it helper or hinder. And now that file is on my desktop here. So it's right here. To put it in my notes, all I need to do is drag it over into the dotted box there. Okay. Or you can say choose file and just select that file. So you can do it either way. So I'm just going to put it over on the dotted box. Now what that does is it takes that file and just loads it into your browser. As is stated in the instructions here, you're going to need to click the upload image to the course database so that when you come back, you will see your screenshot. So again, that's a little bit cumbersome. When you drag it onto the screen, it just puts it in your browser, but I need to actually save it into the course database. So I'm going to say upload image to course database. And now that screenshot will come back, or will be present, when you come back into your notes. If you need to do another screenshot, you can just say remove this one and submit another. So if you accidentally grabbed the wrong one or you messed up, just say remove this screenshot and then submit another. And the screenshot that I took was pretty large, so you can use the scroll bars to see the entire area. Okay, my p-value for my reference distribution was 0.002. So I will go ahead and use that in answering these questions down here. So my p-value is 0.002. So yours might be slightly different than mine, and that's fine. Your reference distribution is going to be slightly different than mine. The decision rule then is the p-value less than 0.05, which it is. So the data does provide enough evidence for the research question, is what I'm going to select. Again, be careful of the decimals here, but 5% is 0.05. So now the conclusion, there's going to be 3 steps to that, or 3 components. There is enough evidence to say, and now I just need the research question, so I'm just going to go up and copy that. So that was provided up above here. Save typing that in. So there is enough evidence to say that 10-month-old infants prefer the helper toy over the hinder toy. And then I want to put the amount of evidence, or a measure of the degree of evidence that I have. So there I'm just going to put my p-value in there. That's how I was doing that. So then there I have the 3 components. There is enough evidence. Provide the research question so we know what we're talking about. And then also provide the amount of evidence that we have for that research question. So those are the 3 components that I'm going to be looking for in a conclusion. Okay, a couple of notes here that I will let you read through. And then the bottom here is something else that was put into the description of this study. And I just want to point that out to you. The color, shape, and order, left to right, of these toys were varied and balanced among the 16 infants. So in other words, the gray square was not always the helper toy. For other people, the helper toy may have been the yellow triangle. Or maybe the helper toy was the red circle. They mixed all the different colors up on whether or not it was the helper toy and the hinder toy. They also mixed up the shape. So sometimes maybe the triangle was the helper toy. They mixed up the side of the tray, the left and the right. Sometimes they put the helper toy on the left, other times they put the helper toy on the right. They mixed all of this stuff up to prevent confounding from being, prevented confounding variables. So no longer is color going to be a confounding variable because they mixed it all up for the different kids. If they would have left the color and the shape and the side all of the same, and let's suppose kids hate the color yellow. So if yellow was always the hinder toy, and infants hate the color of yellow, maybe that's why they weren't picking the yellow one, is because of the color and not because it was the Hinderer toy. So if they didn't mix up the color and the shape and the side, those variables or those elements would be potential confounding variables. So what they said in the study is they mixed all them up. And the reason they did that is to prevent the confounding from taking place. Now, the design process to prevent confounding from this study is very different than the one that we used in the breastfed bottle-fed example. So in the breastfed bottle-fed example, the way that they prevented confounding was that they tried to use a matched paired design, or they did use a matched paired design, where all of the kids were matched up as closely as possible. They did that to try to prevent confounding. Here in the helper-hinderer example, they tried to mix everything up to prevent confounding. So it's important to prevent confounding when we're doing studies. We want to know that the element that we are studying is the reason that we have the differences and not because of something else. So the process by which an experiment is conducted must be taken into consideration when we attempt to try to prevent confounding variables. Okay, that does it then for the case study of helper-hinderer. Thank you very much.